In 1986, the Soviet Union operated a massive nuclear complex located a few miles from the young city of Pripyat. The facility functioned under a systemic lack of safety culture, driven by the intense secrecy and isolation of the Cold War. The plant relied on the immense RBMK-1000 reactor design. Inside this vast core, graphite blocks moderated the nuclear reaction, while ordinary water pumped through the fuel channels acted as a liquid coolant. The RBMK design harbored a specific physics flaw known as a positive void coefficient. As the cooling water absorbs heat and boils into steam, it forms empty pockets or voids. Because water absorbs neutrons but steam does not, these voids allow more neutrons to strike the uranium fuel. This accelerates the nuclear chain reaction, which creates more heat and in turn more steam. On April 25th, the operators at Reactor 4 prepared for a scheduled safety test. The goal was to see if the momentum of a spinning, disconnected turbine could generate enough electricity to keep the water cooling pumps running during a total power blackout. To run a blackout test, the operators had to deliberately reduce the cooling water flow. In a reactor with a positive void coefficient, reducing water creates more steam voids, driving reactivity up. The test parameters were at direct odds with the physics of the machine. The power reduction began on schedule at 1:06 a.m., but a regional power station unexpectedly went offline. To meet evening electricity demands, the grid controller in Kiev ordered Chernobyl to delay the test for 11 hours. By the time the test resumed, the prepared day shift had left, leaving the complex procedure to an unprepared night shift. During that long delay, the reactor operated at a low power state. This allowed a radioactive byproduct called xenon-135 to accumulate in the core. Xenon absorbs neutrons. It acts like a poison to the chain reaction, choking the core and causing the power to drop to a dangerously low 200 megawatts. To combat this poisoning and force the reactor's power back up for the test, the night shift manually pulled nearly all the control rods out of the core. The xenon and the high flow of cooling water were the only things suppressing an enormous spike in reactivity. Hours earlier, the emergency core cooling systems had been disconnected with manual valves to prepare for the test. Despite the 11-hour delay, they were left off. By the early hours of April 26th, the reactor was stripped of its automated defenses. It was operating in an intensely volatile state, maintained by a skeleton crew attempting to complete a delayed administrative checklist. At 1:23 a.m., the test began. The steam to the turbines was shut off, and as the turbines spun down, the electrical power to the main water pumps dropped. The water flow into the immense reactor core decreased, heated up rapidly, and violently flashed into expanding steam. Because of the positive void coefficient, this sudden lack of liquid water caused the thermal power to surge. The nuclear reaction intensified, instantly vaporizing the remaining coolant. At 1:23:40, an operator pressed the AZ5 emergency shutdown button, dropping the control rods back into the core. But the tips of these rods were made of graphite, which actually increases reactivity. Their insertion triggered a massive, localized power spike. The intense heat fractured the fuel rods, rupturing the pressure channels. The escaping high-pressure steam tore the 1,000-ton upper cover plate entirely off the reactor, exposing the core to the open air. 2 seconds later, a second, far more powerful explosion, estimated at 225 tons of TNT, ripped through the building. It scattered red-hot fragments of the graphite moderator across the facility and permanently terminated the chain reaction. The explosion represented the sudden, violent release of the core's total potential energy, bypassing every safety mechanism designed to contain it. 2 workers were killed instantly by the blast. Within minutes, plant staff and local firefighters arrived to extinguish the burning chunks of graphite scattered across the roof. These first responders stood in intensely radioactive fields with no protective gear. Over the next few weeks, 28 of them died agonizing deaths from acute radiation syndrome. While the visible fires burned, the open reactor core began a silent 10-day release of dangerous fallout. Plumes of microscopic radioactive isotopes drifted outward over the sleeping populations of the countries of Ukraine, Belarus, and Russia. It took 36 hours after the explosion for the Soviet government to establish a 10-kilometer exclusion zone. Only then did they evacuate the 49,000 residents of neighboring Pripyat, who had gone about their day completely unaware of the contamination. While the fallout drifted across the border into Belarus and beyond, the Soviet state remained silent. This initial refusal to acknowledge the accident transformed a local industrial failure into a mounting political crisis for the Kremlin. The government did not publicly acknowledge the disaster until April 28th. They were forced to do so only after safety engineers at the Forsmark Nuclear Power Plant in Sweden detected a dangerous surge in radioactivity on their own shoes and traced the wind patterns back to the Soviet Union. With the cover-up broken, the Soviets mobilized an enormous cleanup effort. Over the coming years, more than 500,000 personnel, known as liquidators, were deployed to the site to decontaminate the surrounding landscape and secure the ruins. Their first critical task was draining the bubbler pools beneath the reactor. The melting fuel had formed a radioactive lava-like substance called corium. If that 1,200-degree mixture melted through the floor and hit the water below, the resulting steam could have caused a secondary, highly contaminated explosion. By October 1986, the liquidators hastily erected a massive concrete sarcophagus directly over the destroyed Reactor 4. This sealed the remaining highly radioactive material inside to protect the crews working in the adjoining, still functioning reactors. The cleanup cost an estimated 18 billion rubles, virtually bankrupting the Soviet Union. The logistical requirements of the mitigation effort forced a level of transparency that was previously impossible within the Soviet system. A 1991 state safety report looked past the operator errors that triggered the blast. It exonerated the night shift from violating operating policies, noting that specific safety principles regarding low-power hazards and the reactor's positive void coefficient had never been articulated to the operators by the state. This data visualization illustrates the long-term epidemiological findings compiled by the United Nations. While it shows a distinct spike of approximately 5,000 thyroid cancers among those exposed as children, the data confirms no broader evidence of a major public health impact attributable to radiation exposure 2 decades after the accident. Despite those specific medical findings, the socioeconomic devastation was vast. The exclusion zone eventually expanded to a 30-kilometer radius, displacing 350,000 people from their homes and removing vast tracts of agricultural land from production for the foreseeable future. Former Soviet President Mikhail Gorbachev later observed that the nuclear meltdown at Chernobyl was perhaps the true catalyst for the collapse of the Soviet Union, exposing the fatal flaws in an opaque and rigidly controlled bureaucracy. Between 2016 and 2018, an international coalition completed the new safe confinement. This massive steel arch was slid over the aging 1986 sarcophagus, ensuring environmental protection and finally allowing crews to safely dismantle the remaining radioactive debris. Today, Reactor 4 is completely entombed. The disaster it caused forced an isolated industry into international cooperation and demonstrated the devastating consequences of building a machine and a system without a culture of safety.